Okay, well, this particular work was done by a colleague of mine, Wayne Kelly, and myself. As some of you will be aware, we had been doing .NET compilers for a little while, and I had done both verified languages, and I also did an unverified unmanaged data language just to see what the issues were there. And to my regret, the book I wrote on compiling for the .NET Common Language Runtime was written before I did the unverified language, so it's fairly light on in that area, and I'm looking forward to doing a second edition one day which actually catches up on all of the stuff which in principle should be in a book on compiling for the whole variety of .NET, and not just for the particular strongly typed, fully verified area that I did deal with. Well, Ruby, of course, deals with the third category of language which it's possible to implement on the Common Language Runtime, and it involves some unique problems. And the particular language which we chose to have a look at in order to try and understand what the issues were and are was Ruby. And it turns out that that's actually quite I'm not quite sure that it's a good example to have chosen, because it has some problems that are unique to this language rather than to dynamic languages in general. But just to give you an overview of the talk, I'm going to talk briefly about Ruby for those people who don't know about the language. I'm going to talk about the particular compiler, and spend most time talking about the implementation issues that are involved. And then I'll talk about the current status. We've just gone to preliminary release on the language, but it's a long way from being finished. And then finally I want to do the inevitable commercial break at the end and talk about some of the infrastructure spin-offs, the tools that we created as part of the project, which are available as part of the project, but also as general open source stuff for other people to use however they wish. So let's talk about Ruby. Ruby is an object-oriented scripting language. Its originator was a guy known everywhere as Mats, Yukihiro Matsumoto, and the language actually had a fair bit of usage inside Japan before it kind of got exported to the rest of the world. It's got some features that are much in common with other dynamic scripting languages, and it's got a few things that are different, including things that create technical issues for the implementation. And along with most of the other scripting languages, it's got a user community which can be fanatical at times. And I'll say no more, because there may be some of you good people out there in the audience. But it's an interesting language. So, okay. Well, this is a pretty strictly object-oriented language. One of the first things that my group and I did when we became interested in doing dynamic languages is we did a feasibility study of doing Perl. And Perl is, I think this happens to all languages, particularly dynamic languages, but the older they get, the more they sort of accrete like moss on a tree. and because Perl is the oldest of these languages, it's probably the scariest of all to try and implement because there's just so much stuff there. And it had object orientation added on as a kind of afterthought at the end, whereas Ruby was object-oriented right from the beginning. It's got a pretty straightforward, conceptually a straightforward object model. Everything is an object, or pretty much everything. Okay, so the things that are a little unusual is that it allows methods to be attached to individual objects as opposed to just attaching methods to classes. So in other words, it has singleton methods. And method calls can optionally be passed a block when they're invoked. And a block is you can think of it as being a kind of lambda expression. Or you can think of it as being if you are old enough to remember Algol 60, you can think of it as a thunk that gets passed in for a call by name. And the inside the callee, if you have a block passed in, whenever the callee executes yield, then the block gets executed. And it's widely used, of course, for iterators. The language has continuations. I don't have a very good handle on the question as to how widely used continuations are. It would certainly, and one fervently and devoutly hopes that it's not very often, because these things are a dog to implement. And I should be upfront, Ruby is not a language which executes terribly quickly in the existing implementations. And if you do continuations, whether you do it on the existing compilers or whether you do it with our compiler, it's going to be very slow. Okay, so as far as the object model is concerned, this is a language where each class has a single superclass, but you get most of the functionality that you would get otherwise with multiple inheritance by allowing an arbitrary number of modules to be mixed in to, so you've got mix-in inheritance. We'll have a look at that particular model later on. So the central concept of the type system is what the Ruby people themselves like to refer to as duck typing. And it's a kind of subtle joke, particularly for somebody to have made whose first language was not English, because it refers both to duct tape, which, as you know, holds the universe together, and also the old adage about if it walks like a duck and it quacks like a duck, then it is a duck. And certainly the rule here is if it flies like a duck and it quacks like a duck, then we'll call it a duck. So the idea of the names of types is not a terribly important concept here, but it's behavioral. Well, in terms of trying to implement this language, the first step, I think, for any language on the CLR or any other platform for that matter, is to decide how to map the types of the various entities of the language onto the type system of the CLR. And that indeed is the thing which you do spend most of your time on, particularly with languages of this kind, because the mapping turns out to be rather non-intuitive, even on the basis coming from having considered other dynamic languages. The other issues, which as well as the usual issue of closures, which I guess most dynamic languages pose. Along with the functional languages, you have the particular issues that have to do with blocks and continuations, and dealing with the dynamic nature of the inheritance hierarchy, where the inheritance hierarchy can kind of change, and name binding can change under your feet. And from a practical point of view, the challenge which we would most like to make some progress on in terms of a contribution to the sum of knowledge on how to do dynamic languages on the CLR, the issue that we'd like to solve is how to do interop in a way which both allows users of the dynamic language to get at all those goodies that are in the base class library, so that you don't have to reinvent stuff. And if you've got some methods in the base class libraries that can do the heavy lifting for you, you want to be able to get to them, but also you want to be able to, in both directions, be able to use stuff from other dynamic languages and have other dynamic and indeed static languages call into Ruby when there's some good reason to do that. So, all right, let's talk about Ruby.net, the project. At my home base, Queensland University of Technology, we have been constructing a Ruby compiler for, I don't know, a bit over 6 months, I guess. And this is a compiler for Ruby rather than an interop wrapper or just a managed port of the interpreter. And I should have said earlier that the existing implementation of Ruby, the one that Matt himself wrote, is an interpreter, and it's not your usual dynamic language compiled to byte codes and then interpret the byte codes. It actually constructs a syntax tree, and the interpreter walks over the syntax tree in order to perform the operational semantics. So what we are doing a compilation. We're compiling down to byte codes. That is, sorry, to IL. So we're actually constructing program executable assemblies and executing those, even for the case of eval, which I'll talk about later. The compiler went to its first public release a few weeks ago, I guess, a month or so ago, and along with all of the stuff which we've done in the last few years, this is an open source project, and it's released under a license which is most like the FreeBSD license, and just to make clear that this isn't GPL.
So John, you mentioned that this implementation is a true compiled language. You mean you wrote a parser to parse Ruby syntax and
Sure.
produce IL
Yep.
that is consumed by the CLR directive?
That's right. Yep. And, yep. Oh, yeah,
So
yeah.
My question was, John mentioned that this was a real compiler, and as opposed to a port of.
The question was just clarifying that this is a compiler. The system reads Ruby source, it emits IL, and constructs assemblies, and it does separate compilation so that you can pre-compile Ruby files, a whole bunch of them, and you can then you can do a mixture of Ruby that you haven't seen before, which gets compiled on the fly, and the stuff that's been pre-compiled. So yeah, it's PE files. Okay, talking about the implementation issues, And I don't want to whinge like compiler writers always do, but I'm going to at least briefly. The major problem with Ruby, as with a lot of languages, is that there is no definition of the language, right? If you want to know what this language does, you get the implementation, you perform experiments on it. And this is a nightmare, of course, for compiler writers. I don't know what the answer is some years ago, and I was pleased to see Susan Eisenberg somewhere here. She and I sat on an ISO language standardization committee some years ago, and we were a fair bit younger then, and we were determined that we weren't going to have this problem anymore, and we were going to do a formal definition of this particular language. And we ended up with a standard which we all jokingly referred to as the BFD, the big fat document. It was 1,000 pages of VDMSL, and that really didn't solve the problem either. But okay, so it's a problem. The best reference you have for what Ruby is supposed to be is a book that's universally called the Pickaxe book. Unfortunately, the Pickaxe book doesn't tell you everything about Ruby, and some of the things it does tell you are simply not correct. So, but that's normal. You know, nobody ever wrote a book that thick without making lots of errors. So this is a problem which you have to solve. You end up doing a lot of experiments. As it turns out, yeah.
Isn't there a set of tests that your compiler is supposed to pass?
That's right. That's exactly it. Sorry, Jim. The question was, isn't there a set of tests? Yes, there is a set of tests, and when you pass all the tests, you can say that your implementation is moving in the direction of correctness. Okay. Well, as it turns out, the thing that saves us here is the test suite, A, and B, the fact that the original source of the existing Ruby compilers is available under licensing conditions which do allow you to experiment with it freely and use the ideas that are involved. And that is extremely helpful, because things like the way that in which names are bound inside the language are sufficiently complicated and indeed arbitrary in terms of the design decisions that have made, that unless you follow the algorithmic structure of the original very closely, it's not at all clear that you can get precisely the same semantics as the original. So our strategy has been to closely follow the algorithmic structure of the original. Once we are happy that we have the semantics correctly, then we're quite prepared to say, okay, well, now that we understand exactly how this works, we can substitute whole blocks of code that we can prove will produce the same result, but quicker or more elegantly. Well, everything in Ruby is an object with a well-defined class, whatever that means, as I'll explain in a moment. Everything has a class. However, it turns out to not be a very good idea to try and say, well, okay, let's map all these classes to instances of the CLR system.type. And one of the reasons for this is that classes are extensible in a way which is kind of different to the way that, say, partial classes work in C#. You can have a whole bunch of files, of modules, which declare different parts of the same class. And it's not like in C# where the compiler assembles all these partial classes to create a class. When you first load a module, now these in our case, have been already compiled. So when you load the IL corresponding to a particular class definition, you get that class that you've already seen. Later on you may load another file which says same class name, and what happens is then that you pick up the features of that class and you say, I've already seen this class, okay, you just add the features to the class you've already got. So a class grows dynamically. So the code that you compile, when you compile a Ruby module, doesn't define a class. It simply produces code that lazily constructs a class if you don't already have one of that name, but otherwise if you already do have a class at runtime with that name, you add features to the class based on the code that you've got. So compiling a class definition doesn't define a class at the CLR level. It just adds to a class that may already exist. Well, so all of the classes that we have in a Ruby program end up being represented by a small number of different classes at the CLR level. We have a class called ruby.object. We have a couple of subclasses of that, ruby.string, and a number of others. In fact, ruby.class is a subtype of ruby.object. So there's a small number of kind of built-in templates at the CLR level. It's actually, I trust we shan't have difficulty talking about this, but there is an issue when I stand up here and spout on about classes, because you have to be clear. I have to try and be clear when I'm talking about a CLR class and when we're talking about a Ruby class, because the two sort of don't map.
But you did say, John, that a Ruby class is not, there's not a one-for-one with a class that exists in CLR. It's just an abstract. Ruby class becomes an abstract construct that may or may not later on become a class in CLR.
Well, the question was the relationship between a Ruby class and a CLR class. There is a CLR class that we use called ruby.class. Okay. Maybe hundreds of Ruby classes will use exactly the same type for the representation at runtime. It's just they have different dictionaries attached to them, right, at runtime. Well, not everything gets represented. Not all objects at the Ruby level get represented by objects at the CLR level for reasons that have to do with efficiency, I guess. And the exceptions are we have the Ruby classes fixed num, true, false, and nil all get represented by boxed primitive objects at the CLR level, so that this, I guess, saves some storage. So if you have a fixed num, for example, if you do some operation on it which turns it into a big num, then suddenly you create a ruby.object object for it and do some marshalling. Also, interop objects do not use ruby.object for their representation, as we'll see a little later. Well, since we have, in fact, three kinds of things in the CLR at runtime that represent Ruby objects, we have boxed primitive objects for things like fixed nums, we have ruby.object objects, and we also have interop objects. In fact, all that you can say for sure about an arbitrary Ruby value is that it can be represented as a CLR system object. And in order to retrieve information to call methods on these things, we have a method called class of, which takes a system object at the CLR level and pulls out the class object, the Ruby class object corresponding to that. And here's the signature of it. It's a static method. It takes a system object and it returns a Ruby class. Now, for those particular Ruby values that are represented by Ruby objects, which of course is the majority of them, the class object is found by a field in the ruby.object object, and it's called class with a K, and so that you have this, the code inside class of simply says, is it one of these special objects? If it's not, then just return this dot class with a K. Now, in the case of an interop object, which is the interesting one, there may not be a Ruby class object already constructed, right? If you have been handed something which is just a CLR object from the base class library, a collection class or something like that, if you call class of on such an object, then you create a ruby.class object on the fly and populate its dictionary by reflection. Okay, so that's the key to how the interop works. Another of the peculiarities of, yep. Oh, okay, sorry about that. One of the peculiarities of Ruby is that Ruby classes do not have instance variables, they simply have methods, whereas objects have instance variables. So if you dynamically define instance variables on an object, then they apply to that object only. So this implies that Ruby objects have need a dictionary for the instance variables which have been defined on them, and the class object has a dictionary of methods which you look up. So you've got, if you have two values which are ostensibly of the same type, then if they have instance variables at all, the instance variables may very well be different. Furthermore, if you have two objects which you create with the same constructor so that they belong to the same class, then as they get used, they can have singleton methods defined on them, which means that they no longer have the same set of methods. Although, if you ask these two objects, which now have a different set of methods, what is the name of the class to which you belong, they will still give you the same name. All right, now name binding, I guess, is the key to understanding how this whole system works. And in order, if you invoke, dispatch a method on an object, then the order in which the lookup proceeds is that the system first attempts to find a singleton method belonging to that particular object. Failing that, it goes to a method of the class that was declared when the object was created, which of course itself is dynamically bound, so that if you say new of foo, then you look up to find out what class is foo at this particular point in the program. You then look at mixed in modules, and then you go to the superclass and repeat until you finally get up to Ruby object and the mixed in module kernel, which is where it all stops. Now here's an example which you probably can't read, but I'm going to zoom in a moment. But this is interesting because here's a little snippet of Ruby here. We say class C inherits from B, and we include this, mix in this module M. That's all that there is in the class. This is the complete web of type of class objects that definition generates, and this has all of the kind of built-in infrastructure here. There are 4 kinds of things here which I have color-coded. There are ordinary classes on the top. You have proxies here, which I'll explain in a moment. You have modules here, which are the things you mix in, and then you have singletons. Now, the hierarchy for objects belonging to this class starts off with the module C at the top. Let me go straight away to the zoomed in one. Okay, here's module C. Here's the mixed in module, which you access via a proxy for a reason I'll mention in a moment. Here's the B that you inherit from. Here's object that B inherits from implicitly, and here's kernel, the proxy for kernel, which is mixed into object. Okay, the reason that you need a proxy here is simply that this same module, M in this case, may be mixed in to different classes, so that and given that if you see here, you've got the super chain which runs down as you do your name binding there. You can't have a module appearing in 2 chains because that would sort of foul you up. So you have a proxy here which just points through to the name. Now the singletons appear for 2 reasons. The singleton classes appear if you generate singleton classes, singleton methods for a particular class, but it also, singletons appear as the meta class for every class that is defined. So every class, if you ask class of on a class, then you get the meta class of the class. It's a concept which I guess is familiar to all you old small talkers out there. Okay, now just to show you what that would look like if we had singleton methods. If we have an instance of that C inheriting from B, and we do some singleton methods on it, then you just get a singleton class stuck above that, so that your name binding runs down this list here looking for a match, and then says nothing doing if you run off the end without finding a matching name. Well, the implementation of methods is, once again, cannot use directly the infrastructure of the CLR. And the reason for this is that the receiver of messages is not of certain type. In other words, the object itself may be represented as a boxed primitive value. It could be Ruby.object, or it could be an interop object. So the receiver is an explicit, the 0th parameter of calls which occur in the IL as static method calls. So that the arguments that get passed are the receiver as argument 0. You then have some surrounding scope. You then have the optional block, and you then have in principle an array of arguments which are of type object. Well, in the original implementation here, Ruby objects are accessed via function pointers, which suggests that a kind of cognate way of doing this on the CLR would be to use delegates. Turns out that delegates don't really do it for you, because you would like to specialize the methods so that the very commonly occurring case of methods of small fixed arity, you don't want to have to construct arrays of arguments and pass them in. So you would like to specialize for these small number of argument cases. Instead, what we have done is to define a new CLR class for each method, each of which derives from method body, which is a built-in CLR class. Now, the reason for doing this is that method body has a whole lot of built-in methods for calls with 0, 1, 2, 3 up to 9 arguments, and then a call with n that takes an array of arguments. And so if you are compiling a module, all of those just trap. They just call missing method or wrong arity, so that if you are compiling a method which has, say, 2 arguments, then you override the correct arity, which would be call 2, let's say, and let all the rest go through to the catcher, and that's inherited here. Now here's the code in the runtime that performs the call, and this is the C# in the runtime that does this. If you call a method with 2 arguments, you end up doing call public 2. There's your receiver. Oh, there's the method ID, which at this stage we're just using the strings for. There's the optional block, which is just a procedure, and here's the 2 arguments. We look up the method through this find public method, which is the thing that goes through that inheritance chain trying to find a match. And also checks that it is a public method and that it's accessible. And you then perform call 2 on that. Now, if it turns out that the method that you've bound to doesn't have a call 2, because it might require, say, 1 or 3 arguments, then you just drop through to, well, this is if you don't find it. Call 2 will drop through to the inherited method from method body in the case that the arity is wrong. And I should mention Ruby doesn't have overloading of methods. All methods are potentially vararg methods, but you don't have overloading on arity. Well, instance variables. The instance variables, as I mentioned, are characteristic of the object rather than the class, so that each object has a dictionary, which given that most objects don't have instance variables, is lazily allocated. And as you would imagine, the instance variables are just attached to the dictionary dynamically as you pass definition points. So let me quickly skip over object instantiation. Object instantiation is performed by invoking the new procedure on the class variable, and I just point out that this name here is that's Ruby that you see here. So at the CLR level, what happens is that you look up foo in the current context, so that if this all happens inside a loop, you don't necessarily get the same foo each time through. Now there is the possibility, of course, that you have classes that don't generate Ruby objects, but instead generate, say, subclasses of Ruby string. And so it's the way in which that is catered for is that if you have a super type that has an allocator procedure defined on it, then you will get an allocation through that procedure. Otherwise, you will get just the standard Ruby object. All right, finally, local variables. It would be nice to use the CLR mechanisms for local variables to deal with local variables in Ruby, but that turns out not to be possible, or at least not a good solution, because of the fact that these local variables will be captured in closures by blocks, so that we have explicit frames which are allocated by the compiler with named fields, and these named fields correspond to those local variables which do get captured or potentially get captured by blocks. So it turns out that you have three different places that local variables can end up, and the three cases are: if you have a local variable that may be captured by a closure, then it goes into an activation record which may persist after the method has returned. If you have local variables that you can prove don't get captured by closures, then you can use CLR local variables and get a nice gain there. And the third possibility is that you get dynamically created local variables that arise from the use of eval. Now, those have to go into a dictionary at runtime in the activation record because they're accessible to eval, but the compiler can't know about these because they occur as a result of runtime compilation. All right, blocks. One of the tricky things about blocks is that they give you this nice semantics for iterators and so on, but there's a peculiarity of them which makes implementation interesting. And that is that if you have a block that has a return in it, for example, if you have a return in a block, then when you call yield on that block, if the return is executed, the return is not from in the callee. The return is a non-local return into the method in which the definition of the block where the closure was taken. Now that is pretty strange, and it implies that the runtime has to cater for non-local go-tos effectively, and a consequence of that is we use the exception handling mechanisms of the CLR to unwind the activation records, and this in turn has an interesting consequence because it means that every call at the CLR level has to be wrapped with a try block. Now, if you wrap a call in a try block, it means that the IL stack must be empty at the entry to the try block, which means you have to unnest the method calls so that if, for example, you have, as you almost invariably do in languages of this kind, if you have argument evaluation which involves method calls, then you've got to evaluate the argument, move it to a temporary so that when you call the next argument evaluation that the IL stack is empty. Okay. All right, just a note about how we're doing eval. Eval is the normal dynamic language runtime evaluation, takes a string and executes the code. In this particular case, we are being uniform about this. We take the string, we take well, in order. You construct a representation of the current runtime environment. You grab the string, you invoke the compiler to compile it, and it will have references in the assembly that you create to the currently running assembly. We write out the IL to a memory stream using Diane Corney's per WAPI module and immediately load that, and then we execute it. So we're not using compilation sort of in advance and then using interpretation for eval. We're using compilation for everything. All right, current status. The current implementation has concentrated on the core language. That is, Ruby consists of two parts, really. There's the core language, which has a number of built-in libraries, and it has the so-called standard libraries, which are not part of the language. They're just stuff that normally comes bundled with it. We have done the built-in language with a number of exceptions that I'll mention in a moment. And there's a set of tests for all of that functionality. There's about 860 something tests, and we now, 860 tests. We now correctly execute all of those. There are some features that we haven't implemented at this stage. We haven't done continuations. We've got a prototype, but we don't like it much, although it works. We haven't implemented threading at this stage. We think that's kind of orthogonal, and there are some issues posed by that indeed. We do eval, but we haven't implemented the tainting system, which is, of course, absolutely essential for the security system, but we just haven't done that yet. That isn't a problem. The interop system is at a very early stage, and we're still doing design, in fact, on the interop. And we haven't paid any particular regard to speed at this stage. And that's a bit of an issue at this stage, because Ruby itself, the existing implementation, is notoriously slow, and we are equally slow. We have lots of possibilities for speeding it up. For example, at the moment we're still using strings as method IDs, which will obviously have a big performance hit when we go to ordinal identifiers. But we simply don't see that as an issue for the functionality. And the other area in which great gains can almost certainly be made in performance have to do with the caching of method bindings. So at the moment the performance seems about comparable with the native code interpreter. It's a bit faster in areas, a bit slower in others.
John, what was the original Ruby written in?
It's in ANSI C, and it's got set jumps and long jumps everywhere, which makes me feel a little better about using catch and throw. Okay, let's talk about some infrastructure spin-offs.
One more question. Why not port it? What was some of the reasons why not port it from C# or C++?
rewriting the interpreter in C# would have been a possibility, but in fact, John Lamb's going to say something more about this, I guess, later in the week. But the trouble is, if you look at the ANSI C, it doesn't look like the kind of ANSI C that you can rewrite as C#. And it's set jump, long jump everywhere, and unions like you wouldn't believe. So, okay, let me do the promised commercial about tools. One of the very first things we did in the Ruby project, once we realized that we were going to have to stick pretty much to some of the existing code in order to make sure that the functionality was the same, we had to somehow use the parser.y file to generate the abstract syntax tree. And so the first thing that we did, or rather Wayne Kelly did, was to write a program called GPPG, which is the Gardens Point parser generator, which is a YAC lookalike, which produces C#. We've now completed that particular circle. I'm about to release Gardens Point Lex, which is an entirely new implementation of Lex functionality, which again produces C# and is particularly constructed to work with GPPG. So those two will be together. GPPG, right from the start, correctly reduction for reduction equivalent with Bison over the Ruby grammar. Unfortunately, if you pointed at any other file that was incorrect, it fell over. So there's been a fair bit of work done on that. And we're using Diane Corney's PerWappy, which is the P reader writer, which again has had a lot of development done on it. But one of the things that the GPLex GPPG combination does is it's got some extra tweaks. We've got a version of it which does extra tweaks which are aimed at the colorizing scanners that Visual Studio requires. And here's a screenshot of a Visual Studio plugin for the Lex language itself. I'm being waved at to wrap up, so let me just point out a couple of features here. Embedded C#, here's the Lex language itself. The yellow bits are regular expressions. This solves the problem that every Lex user has, that you write Lex, you write a file, you submit it to Lex, it says the syntax is crap. So you fix the syntax, you run it, it says, yep, that's okay, and then your C compiler says you don't have matching parentheses. So all of this, you actually have enough syntax analysis to get both the C# and the Lex right. It's magic for those of us who have been totally contaminated and can't write code anymore without Visual Studio to tell us when we stuffed up and pressed the wrong key. So it'll be up there on the web within a week or so, and it's real cool. And in fact, I can do demos of that later offline if anyone's interested. Yeah.
The tools that resemble Bison, why wasn't LR used?
LALR. So,
ANTLR.
oh, Antler. Well, the task that we had was to use a .y file. So, I've always, for the last 10 years or so, I've almost always used Hans-Peter Mossenbock's CocoA when I needed parsers and scanners. But the specification for the Visual Studio task was to do Lex and YAC lookalikes. So that's what we did, and it's kind of cool. So I hope you all like it. Okay, that's all. I think we're out of time. So thanks very much for your attention. I'm happy to talk about this offline during the week.